Okay, so good. Welcome to calculus. This first few minutes is just basically an animated version of the syllabus. I'll present it as animated as possible, and we'll have nice pictures and drawings on the screen. You can read the hard copy of the syllabus. Actually, you can read an electronic copy of the syllabus on the website. If you want a hard copy of the syllabus, then download the electronic copy and print it out. Okay? If you have questions, feel free to ask them. Otherwise, sit back, relax, and welcome. So how many of you have taken a calculus course before, a calculus course, say, in high school? Okay, how many have taken a calculus course in college before? Okay, how many have taken a calculus course from me before? Okay, good. That's good because I tell a lot of the same jokes on the first day, and so you don't know all those good jokes. All right. What are the goals that we have for this course? Well, we want to model the real world with functions and their rates of change. We're not so much concerned about theoretical ideas in mathematics, but applying those theoretical ideas to the real world. Our goal is to solve problems, and eventually solve the problems which haven't been solved already. If you are one of those people who has taken a calculus class before, our goal is to understand more deeply the concepts of calculus. If you've taken a high school calculus course, that has focused a lot on technique, a lot on problem solving based on templates, but what we're looking for is a deeper understanding based on concepts. Okay, here are some of the people which will be teaching calculus to you this term. This is me. My name is Professor Leingang. If you want to send me an email, you just write my last name and then @courant.nyu.edu. If you want to meet me in the real world, my office is Warren Weaver Hall, 726. Warren Weaver is the Courant Institute. It's over there by Stern. And if you have trouble finding it, send me an email, and I'll send you a link to the campus map. We have some teaching assistants. Suhoon Lee is one of our teaching assistants, and the other one is Adam Stinchcomb. These are not actual pictures of those TAs. They're a little bit older than that. So I run the lecture, as we're in right now, and the TAs run the recitations, and they grade the quizzes and help me along with other things. Okay. If you would like to get in touch with me, you can also always ask questions in class. If you want to ask me a question by email, my email address is right there. If you like other media, you can contact me. You can friend me on Facebook. You can connect with me. Everyone laughs when I say you can friend me on Facebook. As if people over 30 don't have Facebook accounts. I'm on LinkedIn, Plaxo, the usual suspects of social networks. And you can follow me on Twitter. I'm @mleingang, in which I tweet things about math and about life and about jazz and baseball, all kinds of fun stuff. So one of my jobs here, I'm not only just a calculus teacher, I'm vice chair for undergraduate affairs, which means I handle a lot of the teaching in the undergrad program, which means if you have a problem with my teaching, then you need to make an appointment with me to complain about my teaching, and then I will set up a meeting with me to tell me that some students have been complaining about my teaching and advise me to do a better job. But also, I train the other new teachers, not just myself. And one of the things I say that's really important on the first day to establish some kind of rapport, right? To get the students warmed up and make them feel like you're an actual person, not just the person who is keeping them out of med school. And one way to do that is to talk about your home country. This happens a lot with international teaching assistants. I want them to tell where they're from and what they're all about. So with that in mind, I'm going to tell you a little bit about my home country, which is Indiana. Can you guys find Indiana on a map? Raise your hand if you can point to Indiana. Oh, that's not very good. There's Indiana, okay? The capital of Indiana is right there in the middle, Indianapolis, or as people who don't live in Indianapolis call it, Indianopolis. People who live in Indianapolis think that they live in a world-class city, but this is clearly not true because they also root for the Indianapolis Colts. This area up here in the northwestern part of Indiana is known as the region. People who live in the region think that they live in Chicago. But this is also clearly not true because, as you can see, Chicago is in Illinois and the region is in Indiana. So if you like, this is sort of the New Jersey of Chicago, right up there. And we're my Jersey people here. I live in New Jersey, so that's okay, I can say that. Where I grew up, where my parents live now, is down here in the southwestern part of Indiana. Evansville, Indiana, the third largest and fastest growing city in Indiana. All right, this is the state flag of Indiana. You see it has a torch on here, so it must be my destiny to come here to NYU. The slogan for Indiana is the crossroads of America. I think it's because of all the interstate highways that run through it. There are 9 of them, none of them going through Evansville. Famous Hoosiers, a person from Indiana is called a Hoosier. David Letterman, you may have heard of him. Rupert Bonham, who won Survivor All-Stars a while back. Kurt Vonnegut. Eugene Debs, who was a labor activist, ran for president as a socialist while in jail. Also, former Vice President Dan Quayle. Not in my top 5, but he's there. Okay, so enough about Indiana. I want to talk a little bit about Japan. No, about the introductory problems, the things that we'll be looking at, the things that you'll be able to do once we finish this course. Okay. All right, so does anyone speak Japanese? Good, so you might as well believe me. This word is hatsumon, which means introductory problem. And it's the kinds of things that we'll be able to do once we're finished with the course. Here we have a falling apple. And we all know about Newton and the apple falling on his head and how Newton basically invented calculus so that he could study physics. So what we use calculus for is measuring things that change in the world around us, like the position of a falling body. But lots more can be applied. Lots more things can be applied with calculus. There are many more functions in nature that can be measured using calculus. Optimization. Here we have a picture of a leaf, and if you look very closely, you see that there's this pattern of veins in the leaf, and if you look even more closely, you'll see that each of these angles in the branching points of the network of veins is the same. Okay, now you can measure the amount of water pressure in this network of leaf veins, and you'll find out that the angle that's chosen here minimizes the total water pressure in the leaf, which is amazing, right? Calculus can be used to optimize things like that. Now, does the leaf do a calculus problem to decide how to grow its veins? No, but that's another application of calculus. We can use it not just to describe the rational world, but the natural world. Okay. What else can calculus be used to measure? Well, rates of change have lots of different generalizations. For instance, here's a picture of an oil refinery. And oil is one of these scarce quantities, right? And as the price for oil goes up, the demand for oil goes down. Simple laws of supply and demand. But the amount that the demand goes down corresponding to an increase in price can change from market to market. Here are 2 countries. In country A, if the price for oil goes up 10%, then the demand for oil will go down by 1%. And in country B, if the price for oil goes up 10%, then the demand for oil will go down by 0.01%. Okay? Now, one of these countries is China, and one of these countries is Iceland. Which one is which? China is B. Do we have any other answers? Okay, we could also say China is A. How many of you think that China is A? How many of you think that China is B? Okay, he said it first. He must be right. Do you want to explain your answer?
Well, it just makes sense. If China has a lot more development, then they'll need oil no matter what it costs. And in Iceland, if they don't have oil, they'll take a bike or ski.
Right, right. So in economics terms, China has fewer substitutes for oil available, right? So if the price for oil goes up, they don't have as much liberty to choose other things, and so they have to continue to buy oil. All right, so yes, country B is China. All right, and this is a rate of change that measures the what we call the price elasticity of demand for a certain quantity. Okay, what else? Solve. Well, there are tons and tons of problems that can be solved with calculus. This French consortium of mathematicians known as Bourbaki tried to write down in the early 20th century all the mathematics that had been discovered until that point. And what they wrote about calculus was that over 300 years of constant use have not dulled this incomparable instrument. And now we're up to 400 years of calculus, and we're still using it to apply to the world around. Now, this says the objects. Not too much contrast here. The objects, what are the tools that we're going to be studying in this course? The basic idea in calculus is the idea of a function. Functions are all around us. Functions are ways to describe things that change. For instance, the temperature in this room changes as time changes. Before we got in here, before there were other students in here, the temperature was a comfortable, 68 degrees. But now that we have 100 people in here, all of our bodies are warming up, temperature is probably up to about 75. Once we leave, it'll go back down again. But the temperature also changes as a function of position. If I were to go and stand right here, the temperature is one thing. If I were to move maybe 20 feet that way, I'll be outside. Obviously, the temperature is a lot lower. So functions can depend on many different things. We're only going to look at functions of a single variable. That variable could be many things as well. Okay. We can study a lot about functions using algebra, using arithmetic, but eventually those techniques in math are going to break down. We want to basically go to infinity. And to go to infinity, we have to invent a new concept for functions, and that's the concept of limit. All of the concepts in calculus are based on this idea of limit in taking things as close as possible or as far away as possible. One application of the limit is of the derivative. Just to give you a motivation for it, say you're driving along this road, and right about here, your brakes fail. What direction do you go? Well, you go off in a line which is tangent to the curve. How would you measure the slope of that tangent line? It turns out it's measured with a limit, and this is the limit expression that you would have to do. Okay. Now we'll show you how to compute limits, derivatives using limits, but it turns out that there's a nice set of tools for computing derivatives of lots of different functions defined by formulas. Now the Romans used rocks when they calculated stones to take the place of numbers, and the word calculus is the Latin word for stone. So a calculus is a system for computing, and we will learn the calculus of derivatives. Another application of this infinite process, this limiting process, is that of the integral. We will be able to use the limit to find slopes of curves. Integrals allows us to find areas of curved regions. Areas of rectangles, that's easy. Areas of pentagons, a little bit less easy, but still straightforward. Areas of circles and ellipses, we need something called the integral to solve. These two ideas, the idea of finding a slope of a line tangent to the curve and about finding an area of a curved region, are related by something called the Fundamental Theorem of Calculus. One of the important discoverers of the Fundamental Theorem of Calculus is this guy, Isaac Newton, who I already mentioned before. Not only one of the great minds in mathematics, one of the great hairs in mathematics. In this course, you'll learn about the history of math through hair. Okay, the Fundamental Theorem of Calculus relates these two seemingly unrelated concepts, slope and area. We have a lot of options for you to get your textbook materials. One of them is to buy hardcover, one of them is to buy loose leaf, and one of them is to buy electronic. Now, you also need WebAssign access, and so that's available to you in the bookstore as well. One of the bundles you can buy is the textbook with the WebAssign access. You can buy the loose leaf textbook with the WebAssign access, or you can get a textbook on the used market and WebAssign online. Okay? So these are the same announcements on a nice white background, and here are the objectives. So each class, we'll start with an overview of what we're actually going to be doing. We're going to look at the idea of function and learn how to work with functions represented in different ways. There are many different ways to describe a function. If you ask someone what's a function, what they usually say is, well, like x squared. Well, a formula is just one way to describe a function. You could describe a function with values of the function, with a bunch of data, with a function described in words, or a function just described by a picture. Those are all different ways to look at functions. And functions have various properties. One very useful property of a function is its so-called monotonicity, whether it's an increasing function or a decreasing function, or if it's increasing here and decreasing here and neither somewhere else. Okay? So, what is a function? Well, like x squared. No. In math, we take the idea of definition very seriously. When we say definition, we mean that a thing is this if these things are satisfied and nothing else. Okay? If you look up a dictionary definition of a duck, it's going to say like a yellow bird that swims. But not every yellow bird that swims is a duck, right? That might characterize ducks. But there might be other things which are yellow and are birds and swim, which are not ducks. But in math, when we say definition, we mean that it has to have these properties. So a function is some kind of association between objects in one set and objects in another set. What's a set? Well, just think about it as a collection of numbers. Okay? So a function is a relation which assigns to every number in one set another number in another set. Okay? So we usually call the first set the domain, and I've named it D to be descriptive. And the second set, where the numbers go, where the function takes these numbers, that's called the target. And if I look at all of the x's in the domain, apply the function to them, and look at the collection of all those function values, that's called the range. Okay? So the domain is the set of inputs to the function. The target is the destination of these numbers by the function. And the range is all of the images of the function. So let's look at some examples. Well, first I'll tell you why functions are used to model the world. Whoops, sorry. That went the wrong way. Avert your eyes. OK, so here's the modeling process. This is a beautiful diagram that I stole out of Jimmy Stewart's book. Jimmy Stewart, the author of our calculus book, The Richest Man in Mathematics. Well, he's not the richest man in mathematics. He might be the richest man in calculus. He has a 65% market share, which I learned from my conversations with the publishing industry. All right, so we are going to look at real-world problems. That's what you guys want to do, right? We want to solve the problems in the real world. That's why you're getting an education. We can't solve real-world problems. They're too complicated. So let's instead convert them to math problems. And that process is called modeling, substituting mathematical problems for real-world problems. Okay? And that's a skill that we have to learn. Those mathematical problems we should be able to solve, and from those solutions derive mathematical conclusions. Okay? Those conclusions, those things that we discover from the solutions to the mathematical problems, they have real-world interpretations. Okay? So if you, for instance, a falling apple, right? You can come up with a model that should describe the motion of the apple. You can predict how long it's going to take to hit the ground. And then you can time how long it takes for the apple to hit the ground. And that will tell you if your theory is a good one. Okay? Now, we don't worry about experimentation, testing our theories. We are concentrating mainly on the idea of modeling and solving and using those solutions to interpret real-world predictions. Okay? So here is a picture of Plato's cave. How many of you are familiar with the Republic? OK, well, that's a pretty good showing. All students in a well-rounded education should get a chance to read the Republic. OK, so this is Plato's idea of how we visualize the world. He says that we are like prisoners inside a cave. We're chained to only look at the back wall of the cave. And this is the world around us is the back wall of the cave. Behind us, where we can't see, are the forms of the world, the ideal ideas, the concepts of the world are these forms. And through some fancy projection, which in those days amounted to a fire behind the forms, what the prisoners see is not the forms themselves, but the shadows of the forms on the wall. Okay? If I were to take, we have this concept of triangle, right? What's a triangle? It's a polygon with 3 sides. And that's a form. If I'm to draw a triangle on the board, well, this is not an ideal triangle. You notice that this line isn't straight, that these lines didn't even touch. That just suggests a triangle. That's a shadow. Okay? So the shadows are what happens in the real world. That's too complicated. Instead, we deal in the mathematical world among the forms. That's your philosophy lecture for the day. Okay, so these functions, where can they come from? Like I said, functions can be described by a formula or an expression. Anytime you have a variable like x and you do something algebraic to it, you're describing a function. Now, a function has to have a domain. What would the domain of that function be? Well, usually we say we want to be inclusive, and we say that the domain of a function defined by a formula is all the x's which are valid when you evaluate the expression at that x. Or, as we like to say, all the x's that you can plug in to that function and get a number. Okay, so here's an example. We have our function defined by this formula, x plus 1 divided by x minus 2. We're going to find the domain and the range for this function. Okay. Well, just as an algebraic expression, we have a quotient of 2 things, x plus 1 and x minus 2, and when are quotients problematic? This is the interactive part. Yes, sir? When the denominator is 0, right? We cannot divide by 0. Why can't we divide by 0? Anyone have an answer for that? Makes it infinite? Maybe. Undefined.
Can't do it in real life.
Can't do it in real life? Has anyone tried to divide by 0? It turns out if you try to divide by 0, then 1 and 0 become the same number. Okay? Picture that. 1 and 0 are the exact same number. Consequently, if 1 and 0 are the same, then 1 plus 1 is the same as 0 plus 0. And that means 2 and 0 are the same thing. Okay? If 2 and 0 are the same thing, and 1 and 0 are the same thing, then 2 plus 1 and 0 plus 0 are the same thing, and now suddenly 3 and 0 are the same thing. Or if I take any number and multiply it by the equation 1 equals 0, I get that that number equals 0. So the reason that we cannot divide by 0 is that if that were true, all numbers would be 0. Okay? And then all hell would break loose. Right? We can't have a number system with only one number in it. So the fact that we want two different numbers means that we can't divide by 0. So what does that mean for our function? Well, it means that we cannot let x be equal to 2 in order to plug in this number x. Okay? All other numbers are fine. As long as x is not 2, I can divide by that number x minus 2. So the domain of this function, and just to describe the notation here, the domain is the set of all x for which x is not equal to 2. Okay? So the domain is found by using the restriction that the denominator cannot be 0. All other numbers are fine. Okay? Now how about the range? The range, remember, is the set of all y's that come out of the function. The set of all y's that can be written as x plus 1 divided by x minus 2 for some x. Okay? The range is the set of all y's which can be written as the quotient of x plus 2 divided by x plus 1 divided by x minus 2. Well, that's an equation, right? And we want to know which x corresponds to a given y. If you solve this equation for x in terms of y, what you get is that x is equal to 2y divided by, 2y plus 1 divided by y minus 1. Okay? So as long as this expression is valid, then I have an x which corresponds to a y. You know, which number x will let y be equal to 5? Well, I don't know. 2 times 5 plus 1 divided by 5 minus 1. So 11/4 would be the x corresponding to that y. All right, so the range is the set of all y's which can have x's associated to them. And what's the problem here? We cannot divide by y minus 1. Okay, so this equation has a solution as long as y is not equal to 1. That tells us that the range of this function is the set of all y's which are not equal to 1. Okay? Another way to think about this, it's kind of obvious now. When could x plus 1 and x minus 2 divide to give 1? Well, if two numbers divide to give 1, they are the same number. For which x is x plus 1 equal to x minus 2? Well, if that were true, you could subtract x from both sides and get 1 equals minus 2, which leads us to the whole 1 equals 0 road to hell. So that's why this will never be equal to 1. All right, so to summarize, the domain of the function is all x's which are not 2, and the range is all y's which are not 1. Okay? In case you're rusty on the algebra, here's how you solve this particular equation here. We have y equals x plus 1 divided by x minus 2. We want to find x in terms of y. Okay? Well, you've got this fraction here. I don't like fractions. I would rather work with polynomials. So let's multiply both sides by x minus 2. And I have that y times x minus 2 equals x plus 1. If you're following along in the handout, you'll notice that this is one of those slides which is blank. So sometimes when I'm preparing the handout, I don't want to give away everything because I feel like if I gave away everything, you wouldn't have any, you wouldn't have any reason to come to class. So this is something that you would have to either figure out for yourself or come to class. And if you don't have it yet, then you'll get it and you can fill it in. The large version of the slides, which I put online after class, that will have all of the bells and whistles and solutions and jokes put in. So we've got y times x minus 2 equals x plus 1. What is it we wanted to do again? We wanted to find x by itself. We wanted to isolate x as an expression involving y. So multiply it out. Y times x is x times y. Y times 2 is 2y, and we subtract. Right-hand side is x plus 1. Can anyone not see the red dot on the screen? You can see the red dot? OK. If we ever get more lights on, that might happen that you can't see the red dot. If so, let me know, and I'll stop using it to point at the screen. OK, what is it we want to do again? Oh, yes, isolate x. So let's collect all the stuff that has x in it on one side. We'll put the xy here, move this x over to this side by subtraction. Okay, and all the y stuff on the other side. The 2y can go to the right, and the 1 can also stay where it's at. To isolate the x, let's factor out the x from both terms on the left-hand side. So we get x times y and x times negative 1. Right-hand side is still 2y plus 1. And now we're home free. Divide by the y minus 1. And then we have x equals 2y plus 1 divided by y minus 1. Okay. So this course is going to have a lot of kinds of problems like this where you might have an equation and you need to solve it. So if that kind of thing is rusty for you, make sure you look in the book in the appendices. The appendices have a lot of the refreshers. Trigonometry, logarithms we'll talk a lot about, but algebra is something you might want to brush up as well. If the appendices in the book are not enough, on the website I have a few pre-calculus resources which are just available. They're like free checkouts from the library. It's an electronic manuscript. Because you're an NYU student, you have access to this. It's like Schaum's outline of pre-calculus. It's pretty useful. Okay? So if you want extra help with algebra and pre-calculus, there are resources available. Any questions about this? Okay. Yeah?
So then to solve the range, you need to solve for x. And then what?
And then what?
The range.
So the question is, what's the process behind finding the range? Okay? What I did was I took the expression for y as a function of x, and I inverted it so I could find x as a function of y. Why did I do that? Because the range is the set of all y's for which there is an x. If I knew y, what would x be? Okay? So to find out what x should be for any y, I have to invert it. Now, what does this have to do with the range? If y is not 1, then I can solve it, which means that y is in the range. But if y is 1, I can't solve this equation, so y cannot be in the range. Does that make sense? Yeah. Okay? So basically you invert it, and then you kind of look at the domain of the inverse. All right? So what else can you not do besides divide by 0? Well, we know also that you cannot take the square root of a negative number. Right? You can't take the square root of negative 5. Well, you can. You just get a number which is not a real number. We call it an imaginary number. Okay? Not that it's mythical. It's just outside of the real world that we can use. Okay? You can actually do calculus with imaginary numbers and complex numbers, but as you might guess, it complicates things quite a bit. And we'll stay out of that world. So no negative numbers under even roots, such as square roots, fourth roots, 122nd roots, etc. Okay, and the last, well, I don't know if it's the only one, but one other important restriction is that we cannot take the logarithm of a negative number. Logarithms are inverses of exponentials, so to find the base 2 log of negative 6 is like saying what power do we put on 2 to get negative 6? Well, if you take 2 to any power, you get a positive number. So there's no number x for which 2 to that power x is negative. So that's why we cannot take logs of negative numbers. And these rules give us restrictions in what domains can be. Okay, there are lots of other examples of finding domains in the first section of the book. Okay, so that's the deal with functions computed by a single formula. It turns out that you can also use multiple formulas to describe a function. And here's an example where I've done that. This function is defined, we call it piecewise. Why piecewise? Well, we've broken up the domain into 2 pieces, and we've given a different rule for the function on each of those pieces. For instance, in between 0 and 1, these less than or equal to signs say for all x in between 0 and 1, f of x is x squared. For all x in between 1 and 2, f of x is 3 minus 2. Okay? And just to be clear, when x is equal to 1, we're going to use this rule and not this rule. This only applies when x is strictly greater than 1. Okay? So does this make a function? Well, all we need is a rule which assigns to every x in the domain and f of x in the range, and we have a rule. Okay? That rule depends on where x actually is, but there's a rule in each case. So we want to find the domain of the range and the range of this function, and just for fun, we're going to graph the function as well. So here's our graph, which I started with. The domain, well, the domain's all the x's we can plug in. That is, we can plug in anything between 0 and 1, and anything in between 1 and 2, put those together, and we have the entire interval between 0 and 2. This notation here with the square brackets, that means all x's in between 0 and 2, inclusive of the endpoints. Okay, so I made my axes, and now I'm ready to graph. Okay, the first part of this function between 0 and 1, the rule of the function is f of x is x squared. Who can tell me what the graph of the x squared function looks like? Right, the graph is a parabola, one of these things. Okay, we're going to play function Simon Says a lot. If I say Simon says x squared, this is the graph of x squared. Now we're only interested in the part of the graph to the right, to the positive x-axis. So this is the graph of x squared between x equals 0 and x equals 1. And there it is. Okay, so in between 0 and 1, graph looks like that. And when x is equal to 1, I've filled in the point 1, comma 1. Now, when x is in between 1 and 2, what's the shape of the graph on that interval? The shape of the graph is a straight line, and the slope of that line is going to be -1. Right? Just a linear function. Slope is -1, and the y-intercept is going to be 3. So straight lines just have, the shape is like this. Slope is -1, so it's going to look like this. And then we move it up by 3. So there's the graph on the interval 1 to 2. Now I left a circle open here because when x gets closer to 1 from the right, f of 1 is not up here. F of 1 is down here. Okay, so the open circle means that the function value is actually somewhere else. F of 1 is down there. Okay, so now we have the function graphed, and we can answer the question, what is the range? The range is the set of all y's which are values of the function. All of the y's which do correspond to an f of x. So what do we see? Well, everything in between 0 and 1, that's definitely in the range. Okay? How far up does the range go?
2 non-inclusive.
2 non-inclusive, very good. We get everything up to 2, but not including 2, because we have this open circle. All right? So the range of the function is the interval 0 to 2, which is closed on the 0 side and open on the 2 side. That make sense? Okay. That notation with the interval, if there's a square bracket, that means we include that endpoint. If there's a round parenthesis, that means we do not include that endpoint. Okay? Piecewise function, piecewise graph. Okay. So that's about it we can say right now for functions defined by formulas. Different kinds of formulas give us different kinds of functions. We'll talk a lot more about the classes of functions defined by formulas on Wednesday. But to move on now, I'll think about another way to represent functions, and that's numerically. Okay? We do not necessarily need a formula to describe a function. We can just say what it does. We can say, here's its domain, and here are the points in its range associated to those points in the domain. We can do that either with a table, or a diagram, or both. So here's a table. Okay. In the business, we call this a T table sometimes because of the T in the middle. All right? And here we have the x's, and on the other side, their corresponding f of x's. So this is supposed to be a function which takes the number 1 to the number 4, which takes the number 2 to the number 5, and takes the number 3 to the number 6. So if I were to diagram this function, what I would do is I'd make, well, one set for the domain and another set for the range. And for every element in the domain, I would draw an arrow to its image in the range. Okay, so f of 1 is 4, so I draw an arrow from 1 to 4. F of 2 is 5, so I draw an arrow from 2 to 5. And f of 3 is 6. So does this represent a function or not?
Yes.
How many say that this does represent a function? Okay, how many say that this does not represent a function? Sorry, I'm standing behind the pole. How many say that this does not represent a function? How many don't know if this represents a function? How many don't care if this represents a function? Okay, good. As long as that number stays at 0, we're all good. It's okay to not know, not okay to not care. Yes, this does represent a function. What was the rule? Well, we have to associate to every element in the domain a unique element in the range. Okay, so 1 goes to 4, 2 goes to 5, 3 goes to 6. The range is the numbers which are targets of arrows, 4, 5, and 6. Okay, so that one's pretty easy. Let's look at the next example. Here's a different table. And the question is now, what is the range of this function? If it's a function at all. Well, we can do the same thing. We can make a set of blobs, one for the domain, one for the range. And then for each x, connect it to its f of x. Okay, so 1 goes to 4, 2 goes to 4, 3 goes to 6. Is this a function?
No.
How many say yes this time? How many say no? How many don't know? How many don't care? Okay, let me hear from one of the yes people again. I've heard a lot from you, and I'm sure you understand. I'd like to hear from someone else. Another yes person. Where are my yes men at? Yeah.
Every number in the domain has an image in the range.
Every number in the domain has an image in the range.
There's a rule.
Is there a rule?
Not necessarily in this case. But
Okay. There's not a, we don't have an algebraic rule, but what we do have is that each place in the domain goes to 1 point in the range. Okay, and if you look back at the beginning of the slides, that was the definition of a function, that assigns to every element in the domain a number in the range, and so this is a function. The range of this function is 4, 6. Okay, so 1 goes to 4, 2 goes to 4, 3 goes to 6. We know of functions which double up like this, right? What about x squared? 2 squared and negative 2 squared are the same thing, okay? And x squared is a function. So it's all right for two x's to go to the same y. All right, next example. What if 1 were to go to 4, 1 were to go to 5, and 3 were to go to 6? How would we graph this function? How would we diagram it? Well, 1 would go to 4, 1 would go to 5, and 3 would go to 6. Is this a function? How many say yes? How many say no? How many don't know? How many don't care? Okay. No, it was unanimous that this is not a function. And you're all right. This is not a function because 1 is supposed to go to 4 and to 5. Okay? And functions can't have two separate y values. You can't have an x which has two images under a function. Okay? So do you guys see this distinction between two x's going to the same y and an x going to two different y's? Okay? This is not going to be a function because we're undecided where the 4 and the 5 should go. This brings me to my favorite example of a function, and that's a soda machine. Okay? A soda machine is a function which converts your desire into delicious soda pop. Right? I betrayed my Midwestern roots by calling it soda pop. Right? You push a button, and out comes soda. Right? And notice the domain is the buttons, and the range is the brands of soda which come out. If you look at this soda machine, you see that the top two buttons both give Coke. Okay, so our function takes this button to the brand of Coke, this button also to the brand of Coke. You see that we have three buttons which give us Diet Coke, and then looks like Sprite, and then some weird sports drink down below that. And that's all okay, that's functional. So you can press more than one button to get the same brand coming out, but what you wouldn't want to happen is that one button gave you Coke sometimes and Gatorade other times, right? That would not be a useful vending machine, and that's why we care about the functional relationship, okay? The output needs to be determined by the input. Okay, questions about soda? Good. So this is kind of tedious when we think about functions defined by numbers. Students will often ask, why do we care about functions defined by numbers? It's so much easier to just assign a formula to each function. I would much rather think about a function as just x squared or x squared plus 3. Why do I have to think about data? Well, the truth is that data is out there, and we want to use calculus to model the real world. The real world is based on data. So a lot of times in science, they observe data, and then they try to fit it to some nice function defined by a formula. Okay, and then you can do calculus on the formula, but you have to start with the data. Here's an example of a function defined by data. I went to some weather website and I downloaded the temperature in Boise, Idaho in 15-minute intervals over the period August 22nd through 29th of 2008. Why Boise? Why not? Out of Boise, I thought was a place where the temperature fluctuated a lot, especially in August. Okay, so here's a graph of all those temperature values. Any observations you can make just by looking at this graph? What? Sorry? It's a function. That's right, because there's this one weather station, and for every time, there's a unique temperature at that weather station. It's not undecided between, well, maybe it's 23, maybe it's 33 degrees. No, it says it is 24 degrees. So it is a function. Anything you can say about the characteristics of this function? Yeah, it's a sinusoidal, or it goes up and down. And so that would be a useful model for this function, to treat it like it were a sine function. Mm-hmm. Is it continuous? That's actually an interesting question. We would like to treat it like it were a continuous function. We only have values of the function at 15-minute intervals of time. But what we'd like to say is that in between those intervals, the temperature doesn't stray far away. Okay? So if I record the temperature at noon and at 12:15, I think it's a fair assumption that in between noon and 12:15, the temperature is pretty close to either the noon value or the 12:15 value. It wouldn't spike to something else. Okay? So I've assumed this function is continuous. That is usually a reasonable assumption to make. Okay. It is continuous, but it's not very smooth, right? There's a lot of jumping around. And so that happens a lot in data because you have sampling error, measurement errors. So a lot of times what we'll do is use continuous functions to model data, because you can deal with the continuous functions better. Okay. How else can we describe functions? We had so far by formula, by numbers, or by data, right? By diagrams. Those are basically the same thing. You might also see functions just described by a picture. So I'll draw this curve and say, consider this function right here. Okay? Now this function doesn't have a formula. Basically, I told my computer, find me a function which goes through these points and is kind of smooth. Okay? That's a function that we can deal with. You could also have curves which look like this. Okay, this function makes a little loop-de-loop. Okay, curves around on itself. The thing on the right is a relation because we have a bunch of x's and y's related by the fact that they're on this graph, but we do not have a functional relationship. Okay? Give me the 3-word disproof of the proposition that this is a function. The vertical line test. What's the vertical line test? Well, it says if you draw a vertical line through the graph, it can only intersect the curve in one point, at most one point. And this line intersects this curve in 3 points. Now, our definition of function didn't say anything about vertical lines. What did the definition of function say? It said that to each x, there is a single y. Well, a vertical line is the set of all points with the same x coordinate. So if your vertical line intersects the curve, that gives you, in 3 places, that gives you 3 x's, that gives you 3 y's corresponding to the same x. And that's not allowed. Okay? So this is why the vertical line test for graphs can be used to determine functionality. Okay? So that's not a function. What else? Well, it turns out that we can also describe functions just by words. And we'll actually do this several times, we can just think of quantities in nature and use our intuition to decide what the features of that function would be. So we already talked about the temperature as it varies over time. Whether we're in Boise, Idaho, or in this room, we would expect temperature to basically go up and then go down and go up and go down. Maybe it'll get a higher peak and then a lower valley, but it will fluctuate. What else can be measured as a function? The elevation above sea level at a point on the equator at longitude theta. Okay? Words are more complicated, but it's still the same kind of function described in terms of words. Think about standing on the equator at a specific longitude and then walking around the equator, how high you are above sea level, that would describe a function. Okay? It's not always necessary that the independent variable here be time. It can be space. Okay? Here's another function, the utility I derive by consuming burritos. All right? How many burritos? That's how happy I am. That's a function. Don't you guys derive utility by consuming burritos? I definitely do. Okay. So, to recap, how many ways can we describe a function? We covered 4. By a formula, by data, by a picture, and by words. And we need to be adept in treating functions represented all those different ways. Okay, what else can functions, or what can we do with functions? One thing we can do is assign various properties to them. It will be useful to think about functions which have some kind of nice behavior to them. So let's talk about monotonicity. Monotonicity, fancy word. Mono means one, and tone, well, tone is like tone. Okay, well, a function can be increasing or it can be decreasing. It can have the tone of increasingness or the tone of decreasingness. And if it's got that same tone on an interval, we say that it's increasing on that interval. So here's an example of a function which exhibits some monotonicity. Let p of x be the probability that my income was at least x dollars last year. What might a graph of that function look like? What might a graph of this function look like? You have an answer? Yeah?
Downward sloping.
Downward sloping? Okay. Why downward sloping?
Well, because it's the x, that's the income, I guess. If
Mhm.
it's bigger, it's less likely that you're earning that much. So, like, probably didn't earn $20 last year, but it's more likely that you earned more than $5 this year.
Very good, yes. It's very high probability that I earned at least $5 last year. You guys would, you pay tuition and you know how much it costs. And you would estimate my salary to be more than $5? Okay. Would you estimate my salary to be more than $5 million? No, you probably wouldn't. So there's a high probability that I earned at least $5. There's a low probability that I earned at least $5 million. And the further out you go, the less probable it is that I earn that much. Okay? So that means the function should go downward. All right? And I actually took IRS data and connected it to get this kind of graph here. 50% of the people made less than $52,000. 50% of the people made more than $52,000. So the median income in the year that I sampled the data, which was probably 2007, is $52,115. Okay, so that's what the graph of this function would look like. And how do we come up with this? We just talked it through. We decided what kind of properties would the function described this way have, and we determined that it should be this downward going thing. Okay, so that's the kind of function we would like to call decreasing. To be technical, and remember in definitions, that's exactly what we're doing, we're being technical. A function is decreasing if increasing the x decreases the y. So if I have 2 points, x1 and x2, and x1 is less than x2, then f of x1 is greater than f of x2. In other words, if I move to the right, function value moves down. Okay? Another thing mathematicians like to do is create multiple definitions at once. So as long as I'm defining a decreasing function, I might as well define an increasing function. An increasing function would be one for which if I increase x, y also increases. So I have two x's. The one on the right, the one which is greater, is going to have the greater y value. That would be an increasing function. Okay, so let's think now again about my utility of burrito consumption. Would you call that an increasing function? How many think that my utility of burrito consumption is increasing? Okay, good. Okay, how many say not? Well, it kind of depends on what you think about consumption. If you're saying that I'm actually going to sit at a table and consume X burritos all at once, well then yes, after about X equals 7, it might go down. Okay, but in economics, when we talk about consumption, we don't talk about consuming it all at once. We have this property called the insatiability principle. Basically, it means that utilities are always increasing functions. So the utility of consuming 7 burritos doesn't mean at a single sitting. It just means being able to consume that at any time you want. So maybe that's not the best good to apply the principle of utility to, but the idea of insatiability says that the more you have, the happier you are. Okay. Now, the 101st burrito doesn't make you as happy as the first one did, but you are marginally happier. How about that temperature function? Well, we saw the graph of it. It was going up, it's going down, going up, going down. That function is not increasing or decreasing. However, you could look at various parts of the domain, various intervals in time, and you could say that the temperature is increasing on this interval, and then it's decreasing on this interval, right? Sun comes up, temperature goes up. Sun goes down, temperature is going to go down. Though you could find those intervals. Okay. Here are some other functions defined in words. These are physics examples. We did some economics examples. Now we'll do a little bit of physics. Okay. Look at intensity. Let I of x be the intensity of light, x distance from a point. So think about a light bulb. Measure your distance from the light bulb and measure how intense the light is at that distance. Okay, think about that in a little thought experiment. Take the gravitational, next function, take the gravitational force at a point x away from a black hole. Okay, and think about what the graphs of these two functions are going to look like. Okay, well, intensity is going to drop off. Right? If you right up next to the light bulb, you have this bright, intense light shining right on you. And as you back up a little bit, it gets less intense. And the intensity of light doesn't depend on whether you're on the right side or the left side of the light bulb, or the front or the back. The amount of light shining on you is the same no matter what direction you are away from it. What really matters is how far your distance is from it. So what that means is that this function has some symmetry to it. The values on the right-hand side are the same as the values on the left-hand side. Okay, if I'm 3 feet to the right of the light bulb, the light is just as intense as if I were 3 feet to the left of the light bulb. Okay? So this function has a nice property that it's symmetric around the y-axis. Okay, now let's look at the gravitational force function. We've got a black hole right here at the origin. If I'm a little bit to the right of the black hole, then the gravity in the black hole is pulling me towards the black hole. Okay? So if I'm a little bit to the right, the force is pulling me to the left, which means that the force is in the opposite direction, or we count it as a negative number. Okay? So if x is positive, force is negative, pulling me back towards the origin. If x is negative, well, now I'm to the left of the black hole. The black hole is going to pull me to the right, again in the opposite direction of my position. So if x is negative, f of x is positive. And aside from that, the amount that the black hole is pulling me only depends on how far I am away. Okay? So it looks the same, except for the fact that on the other side, it's in the other direction. Okay, now you have to picture this in 2 or 3 dimensions, but it's basically the same thing. The force has a directional component to it. Okay? But for this one-dimensional example, values on the left are the opposite of the values on the right, compared to this example, where the values on the left are the same as the values on the right. So these are useful kinds of functions. We call the first one even, and the second one odd. Technically speaking, a function is even if a value at a negative number is the same as the value at the corresponding positive number. So f of minus 3 is the same as f of 3. A function is odd if f of a negative x is the negative of f of x. So f of negative 3 is the opposite of f of 3. If f of 3 is positive, f of minus 3 will be the negative of that number, f of x. Okay, so can you give me an example of a function which is even besides the intensity graph? Yeah? X squared. Right? If you square negative 3, you get 9, which is the same as what you would get if you squared positive 3. Okay? Any other examples of even functions?
Absolute value.
Absolute value, very good. Absolute value is basically the quintessential even function. It only measures distance from 0. It doesn't measure the direction from 0. How about an odd function? X cubed is an odd function, right? If x is positive, x cubed is positive. If x is negative, x cubed is negative. So if we're playing function, Simon says, this is the graph of x cubed. Okay, walk like an Egyptian here. This is x cubed. X squared is touchdown. X cubed is walk like an Egyptian. And that's an odd function, not because I look funny doing it, but because values on the positive side are the opposite of values on the negative side. Okay? And it's no coincidence that 2 is even and x squared is an even function. That's just a good name, right? We decided to call those kinds of functions even because they resemble even-powered functions. And x cubed or x, y equals x, those are odd functions because they resemble odd-powered functions. Okay, lots of other functions exist, though, like the exponential function or the logarithmic function. Square root doesn't have any negative values to it. So not everything is either even or odd. Okay. So that is the basic state of the game. We're looking at functions all over the place. The basic idea in calculus is the idea of function. We will be representing functions in those many different ways. Okay? And next time what we'll do is we'll look at the different ways or the different kinds of functions defined by formulas. Okay, so I'm all done. 2 minutes early, I'll point out. And if you have questions, I'll be up here. You can come talk to me.